Hello guys, welcome to another episode of Wolfram Talk Show. We are going to code Wolfram Language, Mathematica, doing plane curves geometry today. So let me introduce my keyboard, Glove 80 keyboard, ultimate hacking keyboard. On my website, you can see reviews, and on YouTube, video reviews. And next video, we are going to do this. Okay, it's been a long time. This is Svalbard data hand, Svalboard, Svalbard data hand, a very special input device. I think it's the best. So next video, XR talk show, we'll be doing this. So that is my keyboard's introduction. Now let's go to the let's start to do today's talk show. So let me switch screen. There we have it. Okay, comments. Okay, you ask me questions. Hello, Steel. What's up? Wolfram language coding. Okay, so let's ready. So my keyboard, my Emacs. So I'm using Emacs. The pink window shows all my command calls as I move cursor or delete things or insert things. You can see all the command names on the right and the key I type on the left. I'm using Starfly keys, of course. You can get it free on GitHub. It's part of the GNU Emacs repo. Starfly keys, the most efficient key binding system, and I'm using a Vorak keyboard layout. So today we are going to do some fun thing. Actually, I'm just gonna work on my website, mathematics. Okay, mathematics, extremely interesting subject. I'm gonna work on the project Special Plane Curves, the project I started in 1995 or 1994. Okay, so it's Visual Dictionary of Special Plane Curves. So this website is my most famous popular website, linked by over 1,000 universities back then, 20 years ago. So and they are Asian. If you look at them today, it's kind of Asian, but back then it's the bleeding edge technology using animations. This used to be videos, but now I turned them into GIF because the codec used by the QuickTime movie animation format is gone obsolete. So the video players won't play, so I have to turn them into GIF. So you are looking at hypotrochoid curve. So anyway, so this is, all the spatial plane curves. Okay, they are two-dimensional curves in the plane, and they have tremendous number of properties. So Wolfram language. Okay, so the good, what's good for you? Maybe you will learn some Wolfram language. So let me introduce you Wolfram language. You can see we already started. If you don't know, let me do some introduction. Wolfram language X. Okay, so Wolfram language in depth, you search for that and search my name, you'll find it. Wolfram language in depth. And if you are impatient, you don't want to watch long, maybe perhaps rambling video live stream, you can just go to this my tutorial. Okay, so and if you want a kind of comprehensive, today I'm kind of just doing random. I'm just gonna work on my curves, conic sections, and but if you want a systematic tutorial on Wolfram language, so you can find them on my Wolfram language in depth. So there's some like introduction, how does the Wolfram language work, so there are like over 50 videos, but some of the best I put them here. Okay, so just go to Wolfram language in depth, search for Xali, my name, and you can download Wolfram language for free. It became free about 6 years ago by now. Okay, and so what you get is a Wolfram script, which is like a text-based. For example, turn it back, magnify. Okay, so you can start Wolfram script and you get text-based. So you can watch my video. I have lots of demo, but now we don't want that. Okay, so Wolfram Language, you can download it for free, but they don't have, like, they cannot do graphics if you use the Wolfram engine. So what you can do is that you download, you download Wolfram engine, then you download the Jupyter. There's a Jupyter package created by Wolfram Research, by the company, that allows you to have graphics in the Jupyter notebook. Okay, that is a case you don't want to pay. If you are the open source, like, yeah, I just want free things. But then, I mean, if you are really into it, you can just pay and buy Wolfram Mathematica. That's what I recommend. Okay, so curves. So let me show you some curves. So this huge amount. Involute is used for gears, the design of gears. So what is involute? For example, if you take a string, you wrap it around a circle, and you unwrap the string, that string, the end of the string, will trace out what's called involute. So this is used for gear design and gear design. For example, all these teeth of the gears, you have to be, like, normally, if you don't know anything about gears, you just think of them as like triangles, that should work. But in practice, not really. I mean, the triangles, yeah, it gives you the basic idea, but in practice, if you want to, for example, put this in car, for example, car, you have gears, you need these, you need lots of these. If you just have triangles, they are not efficient. They you need them to move smoothly and with maximum efficiency, right? So in order to do that, you need to find the geometry of the teeth, and that is an application of this involute thing. Okay, so tremendous amount of properties, very interesting properties. For example, this lemniscate of Bernoulli, it looks like that, like an infinity symbol. And here's their equations, polar equation, parametric equation, and many properties. For example, this one, blah, blah, blah. The distance is such and such that, from here to here and here to there, their multiplication product is constant. Okay, something. Okay, you can read it in detail, and how this curve has a relationship to hyperbola. Okay, so and also if you have a torus or donut, you cut it right around there, then that cross section is this lemniscate of Bernoulli. Okay, like the infinity symbol. Okay, but you have to cut it right there, right at the inner border. Okay, so you cut a donut, you have a cross section, and you see all these. They show you how to use gears, linkages. These are called linkages to trace out the lemniscate of Bernoulli, and this is useful if you want to translate a rectilinear motion to a circular motion. So, for example, in robotics, robotic dogs, how their legs are only move in certain way. So you have to use these linkages. So a lot of application, linkage by itself is a field in robotics. So all these, so tremendous interesting things about plane curves. For example, this orthoptics and isoptic. Okay, I wrote this long ago, 25 years ago, 1995, when I was younger, when I was a teen, when I was like a hot shot. So you guys, if you are younger, you don't have nothing to do, you hang on 4chan every day, do something, do something when you are young. So this optic, orthoptic, isoptic, actually, I don't remember what they are. an orthogonal curve is a locus of all points where the curve's tangents meet at right angles. Okay, anyway, so you can so there's lots of information. So today I'm going to one of my project is update this website. So all this website I need to update. So so update this 25 years project. Okay, that's what I'm doing today. I'm just gonna do some plot and some Wolfram language code. Some of them is easy to plot. For example, the thing we want to plot today is, for example, you have sine and cosine. Oh, this one is beautiful. This is algorithmic art or mathematical artwork. Beautiful. They are actually a plot of a 2D equation. They are a plot of this thing. Okay, so let's just show it. Paste it, run the code. There you have it. So it's simply all these points are the solutions of this equation. Amazing. Is it amazing? Is it beautiful? So that's one thing. You can generate artwork, and this is an illustration of sine and cosine. You see, this animation I created like 25 years ago. This is a fundamental illustration of the entire trigonometry thing. Okay, the entire trigonometry is basically just the sine function, sine or cosine. I mean, all the sine, cosine, cosecant, secant, tangent, cotangent can be simply defined by sine. Okay, so but what does the sine function mean? It's captured by this animation. So the sine function is basically just a trace of the basically it captures the circular motion. Okay, circular motion to linear motion. That is the essence of what the sine function do, and therefore the entire trigonometry. Okay, so when you use so all these are done with Wolfram language. Actually, not some of them are not, because for example these two are not plotted by Wolfram because I started to use some other software. But anyway, what we have to do is that for simple plot you can just plot in Wolfram language like you are using a graphing calculator. But some others require programming. For example, this helix projection. You see, when you project the helix like that, then the projection is actually a sine curve. Okay, so that's another way to generate the sine curve. You see, so this is why these curves, plane curves, has tremendous, visually very interesting mathematical properties. You see, you project the helix, then it is a sine curve. Of course, and also if you roll a cylinder with a obliquely cut cylinder, that also traces out a sine curve. And then you also can see sine curve in two-dimensional sine curve. So this is a two-dimensional function. Actually, a function that takes two arguments, x and y, and returns one single value, returns the height. Okay, so the graph of that function is this kind of cubic wave. So it's basically just sine. Okay, I believe this is just sine times cosine. Yeah, sine times sine x times sine y. You get this surface. Okay. In fact, we can plot that. Okay, so do we have it plotted? Yeah. So our job today is simply, I'm just gonna do some plotting. So so for example, plot 3D. Okay, plot 3D that, and what is the sign goes from 0 to pi, okay? Then x goes from 0 to pi, then y goes to 0 to pi, okay? Let's run it. Okay, you got one piece of it. So let's say 4 pi. There it is, okay? So you see we need to update, so that's what I'm doing. I need to update this graph, okay? There is something we don't want because right now you see it's higher than, you know, this. I want them to look like that. So what do you do? So any questions, comments? Is it good? So what I'm saying is that some of them just require simple plot, and while others require some coding. Okay, this one is another beautiful one. I call this one Borg cube. So this is again a simple plot of a equation of three variables x, y, and z, and that equation is this one. Okay, so in fact we can copy and do it. Why is this one taking so long? Taking longer than expected. Oh, okay, there it is. So once you get the graphics, you can actually rotate it. So this is the beauty if you actually buy Wolfram Language. You know, if you just download the free Wolfram engine, you don't get that. But you can then you use the you know, that what's the name, notepad, you know, you can download it free, then you can have this. But anyway, there is an issue, like whenever you rotate they kind of shrink too, because I mean they have to shrink within the yeah, that's, you know, you can fix that by creating a spherical border. But anyway, so anyway, I want, first of all, let's update this graphics, okay? And I don't like this color, okay? I don't like this color. Oh, all you have to do is axis ratio, you know, I mean you see right now they are not plotted in aspect ratio. I mean in what's the name? Okay, let's see. Let's do that again. Mesh style, plot style. Let's click on that. Plot style. Oh, you can change color. Okay. So I don't like this color. Okay. Theme, image size, export image, lighting is always interesting. Neutral, okay. I don't want neutral. So background, axis, viewpoint, aspect ratio, okay. The feature, the thing I'm looking for is aspect ratio 1. Oh, that's the, no, that's the whole. You should be automatic. No, we want with okay, let's look up aspect ratio. we want it to be stretch graphics to fill out enclosing region. Determines the ratio of the actual coordinate values. Okay, so you see from here to here is 1, I mean it's 2, but from here to here is 10, so they kind of compressed it vertically, which is not what I want. So let's see what some examples to fix that. Okay, so wait a minute. The aspect ratio is not exactly what we want. Box ratios, let's see. Okay, let's see box ratios. Yeah, box ratios automatic. I think there it is. Now it's more beautiful. Now it's soothing. Okay, now 3 pi, 4 pi is too much. Let's just say 2 pi. Okay, 2 pi is not enough. Let's say 3 pi. Need a bit more. Let's see. 1, 2, 1, 2. Okay, so it's more aesthetically pleasing if you cut it right on the ridge. Yeah, so instead of you have the flat boundary, so you want to cut it right on the ridge. So you can do that by simply start with pi over 2. Okay. Yeah, but now that's good. Now to put it 4 pi. Okay, that's kind of what I want. Now the next thing is that I don't like the lighting. Okay, so actually copy that. I'm gonna use my, let's see, what is this? Yeah, close that. I'm gonna use Wolfram Language in Emacs. So if you don't know what that is, I have a Wolfram Language mod that allows you to work with Wolfram engine or Wolfram script in Emacs. So you can download it for free. It's here. It's here. Okay, you can download it. So what's the benefit? Well, the benefit is you can use Emacs, so you have the full power, but except you cannot do graphics. But however, you can still edit it easier. But so show in browser. Okay, that's what we plotted today. Yeah, now we want to change the lighting. Okay. Let's see. Copy that. Okay, so do I really want to change? Yes, because that image is like 20 years ago. You see, they don't have alias. But now I want to change color. Okay, I don't like the coloring. So what you do is you just look at the the documentation for plot 3D. Okay. In particular, what you need is an option. Okay, so let's magnify. Plot 3D, you have an option for lighting. Now, lighting is one of the most spectacular thing, because then you can do transparency, you can do specular lighting, like that is reflexive, like shiny. You can do lots of things. So, but you need the lighting. Okay, and you can change the mesh style. Yeah, so this full of, it's okay, lighting. Okay, so this is what we want, lighting option. Automatic, none. Okay, so let's just do this, several of them. Okay, copy. Okay, so we have a bunch of them. We try different lighting. Okay, okay, so lighting, what is it supposed to be? It's supposed to be automatic, or a light, named light, or a sequence of light sources. Okay, possible named light, standard, neutral, accent. Okay, let's try. So that is one of the okay, so yeah, lighting, standard. What's the other? Neutral, accent, 3-point. Okay, let's try this. See what happens. Oh, okay. Nah, this is like nuclear disaster, fire burned out. So this is good, but I don't like it. You know, what we see here is the you see what we see here, it was the standard back in 1990s. So I still prefer that. Yeah, but now you have to. So I don't like this light. So you know, lighting is fairly complicated. So with so you might need to specify 3 light sources. Possible name lighting setting include standard. Standard doesn't do much. Let's turn on JavaScript. Yes. Okay, so you have ambient light, directional light, point light. Each light source SI can be of the following forms. Okay. Wait, why is this? Oh, okay, so directional light, spherical, point light. Okay, so you know, you can just play with light for hours. So you have spotlight, point light, directional light. Okay, so directional light is okay, so it's like infinite parallel projection. Okay, so you give it that, then okay, so you can kind of, so lightning, okay, so lightning, so we can, so here, so we have a directional light here, and yeah, so you don't want that, so but you want this to be a list of things. So here is the RGB color, let's just say red. Okay, and then you give it, what are these two? These are two positions. Okay, so those two are 2 points from, so the light forms a direction from this point to that point. So this is 5555. Okay, so this lighting is like from top to down. Seems like, okay. I don't think I want that. So this is a directional light. Okay, directional light, color and point is a three-dimensional graphics directive that specifies the directional light of color from the point PT to the center of the bounding box. Okay, to the center of the bounding box. Okay, so let's say color red, then you just need one element here, so you don't need two. And where do you want it be? So let's just say above. So 0, 0, 100. Okay, let's see what happens. Yeah. So you are shining a red light on it directly, then you got that. So yeah, and we don't seem to see shadows and all that. Let's see 1 1 what happens. Oh, we do see shadows, but this is very, very strong light. So you have some kind, you have a red light on it from the side. Yeah, actually from the light point is somewhere here, on the x equals to 0, I mean on the plane. So but if we raise it a little bit, see, yeah, you still get kind of that, like that. Okay, so that is a directional light, but then it's just one lighting. Okay, so let's see blue, what happens. Okay, this is like very creepy. Yeah, but that's not what we, so we do want some kind of shadow, or so that will depends on the surface. Yeah, specularity. Okay, so copy that. So let's try this one. Plot style. Okay, so you need plot style. So let's, so you need a plus dial at least, and one of that is specularity, which specifies the reflective properties of the surface. Okay, so let's try that. There we have it. There we have some kind of, oh wow, look, it changes as you move. Let's see, it does. Wow. So the light is not fixed to the surface, you see. Let's see, you see? Quite amazing. So here what we have, we have direction light, and we have the reflectiveness of the surface. And so you need two lights. Okay, so let's actually put two lights. Let's say this one blue. Red is from where? Red is 0, 0, 100. Red is from the top. Okay. Let's see. $100. Okay, that's kind of from one corner, and the other one is from a different corner. Okay, so let's try that. Oops, something is wrong. Oh yeah, you need a comma. Still wrong. Oh. Okay, now beautiful. Now this is looking like a seashell. Yeah, but it still doesn't like give you the natural look. Like this one is actually pretty good. So anyway, I think I need to think about how to do this. How long have I been talking? 15 minutes already. Any questions? Good night, Steel. Okay, so it's like 40 minutes spent just on this simple thing. So you can see you can really spend hours to play with this lightning stuff. But I was surprised that this lighting changed in real time. It wasn't so 20 years ago. So the lightning seems to be not fixed to the surface, which is properly done, because you don't want it to stick to the surface. And so we have to make judgment on, like, artistic judgment. You know, like which one looks better. You know, this doesn't look so right because you don't see the hill and valley. You know, it looks like, you know, just, so you need specularity, let's say 10. It's okay. So you need some kind of ambient light. Okay, so let's go back, let's add some ambient light. So I think we're gonna finish that, and then maybe that's it. We just add some. So here is a point light. Okay, I think I prefer point light instead of directional light. So yeah, so there, direction, we're gonna delete that. So let's see what happens with this. Okay, still not much. Okay, so but now let's add some ambient light. Point light, directional light, lightning. You want okay. You see the there. So you want some ambient light here. Lighting none. Ambient light orange. Okay, let's add some ambient light. What is the ambient light? Blue, red, brown, blue, red, yellow. Let's see what happens if you do yellow. Okay, the ambient light is not. So if you turn lighting to none, maybe. Because when you have lighting, then the ambient light has no effect. So if you turn all the lightings to none, this is no good. What? So what if you take out specularity? No, you do need some kind of lighting. So you see, this is complicated because besides all these different lighting, you can also change the surface color. For example, you can see material shading. Material shading is a three-dimensional graphics directive specifying that the surface that follow are to be drawn with a material, okay, material appearance. And then you can have a color as an option. So you have some examples: aluminum, brass. Oh, aluminum. That's interesting. So then there's plastic, silver. So let's try aluminum or aluminium, as that keyboard guy used to say. Actually, this is very interesting. So let's try iron, because iron is easy to type. And then you have plastic. Okay, so here is the specular reflection, viewpoint, specular diffusion, and light. Okay, let's try this. Okay, material shading, copy. Where do we put that? Okay, yeah, that's not what we want. Material shading, material. Okay, so iron, so that is that. And how do you, where do you put it? Wow, very, very involved. Okay, so you can map it to texture. Lighting 3-point. Okay, material shading iron. Yeah, that's, I don't think that's what, I don't think this will work, but we can try. Oh, it kind of worked. But now it's more crazy. So now you just take out the lightning. Now you just remove the custom lighting and put it to 3-point. Okay. 3-point. You know, the Wolfram language started to have these string-based names, which is always problematic to deal with in a programming language. Like JavaScript also has lots of that. JavaScript, especially with CSS, you had to have a lot of option names that's simply a string. So when that is the case, usually you cannot do keyword completions because, you know, but you see, for example, you don't know what possible options for the material shading except a literal list. But anyway, so let's keep going with this. Okay, so now we actually get some kind of, wow, material shading iron. Let's just magnify. Wow, spectacular. Actually, this is spectacular. Let's just use this. You know, actually, yeah. So consider this like done. Wait a minute, I want to. Okay, so this is iron. Let's say silver. Fantastic. Let's use this. Okay, so this is like consider today's work. Okay, captured. Now let's go back to my curve page. Syntax error showing browser, and we need to go to sine curve. And the surface, wavy surface. Okay, so we're gonna replace that by wait. So you need to add image. That is 1. Okay, so rename it wavy surface. Okay, Yeah, okay, so that, redo it. Okay, remove that and show in browser, magnify, go down, go down, go down, go down. Fantastic, beautiful. Whoa, fantastic. Okay, that's what I'm gonna use. So let's see. Yep, gonna use that one better than this one. This is, you see, this is a difference of technology after 25 years. Okay, so yep, and I'm gonna copy the code. So here's the code, copy it, and just put the code here. Wolfram Language, put it there, syntax correct, and show in browser. So fantastic. I think that's it. We just show this one. That already took 50 minutes. Okay, any things, guys? So next we're gonna do is I'm gonna do this. Okay, next video in 2 days, probably 2 days, 2 or 3, no more than 3. We're gonna do this data hand smart live. I'm gonna show you guys. Okay, and anything else? Do you guys have any questions about Wolfram Language? We're gonna shut down in 2 minutes. So I'm actually pretty happy, so one of these days I'm gonna code this animation in Wolfram Language. You see, when you want things like this, like today, what we did is simply plot. Okay, all we have to do is just type the function name, just plot it, try different color and see what we want. But then you get more involved. Then you have to do visual graphics programming like that. And this one is actually pretty simple too. And this one also, you need to do some kind of graphics programming. And this too. And in all these cases, it's actually pretty simple. But I can show you a more difficult case. Okay, a more difficult case is this one. You see these conic sections, so they are a double cone. Then you slice them with a plane, parallel plane. Then you get that. So this will be more difficult to do, and one of these coming weeks, I'm gonna do one of that. Lucas Smith. Oh, hi. For the moment, I thought you are Luke Smith, the Luke Smith guy, Linux guy. Fantastic. Good night. Okay. Bye, guys. Okay, now I clean up and bye, guys. So sine curve, beautiful. I'm pretty happy with today's result. This thing, pretty happy. Yeah. Okay, so that is that we did today. Close that. What is this? Close that. Conic section. Talk show. Close that. Beethoven. Okay, so the Wolfram documentation. Okay, that's it. Bye.